Hello and welcome to NVIDIA GTC. My name is Subhan Ali, Data Science Developer Relations here at NVIDIA. Today, I'd like to welcome you to my talk, Accelerated Python Data Science with RAPIDS. This is session number SE2619. First, a few housekeeping items. And for GTC, we are using a platform that allows you to communicate. I am available for chat during this session right now. As you can see right here, instead of the name Kevin Berry, you would see Subhan Ali, and then you can go ahead and ask the presenter or moderator right here. So that's during this session right now. I am also available throughout all of GTC and you can do the same thing by finding me on the platform. Instead of Kevin Berry, again, it would be Subhan Ali, searching for me. Then you can go ahead and connect with me by hitting the connect button on my name. So feel free to ping me on the GTC platform. I'm happy to chat however and be helpful however I can. So I actually want to go ahead and jump into the content talk. Data science is is a burgeoning field, and it's a field that's really taken off in the last 8-9 years. In 2012, there was a Harvard Business Review article calling data scientist the hottest job of the 21st century. But anyone who's done data science knows that there's a few problems that are actually posed by it. So the first problem is that it's actually extremely time consuming. Those of us who are familiar with pandas and scikit-learn in the familiar Python format know that it can actually get pretty difficult and painful once you start dealing with very large data sets. And the reason for this is because that pandas and scikit-learn are underlined by CPU architecture. So you're actually limited by the CPU memory and the CPU compute. Second of all, it's costly. It's actually just downright expensive, whether you're doing this, wherever you're doing this actually, on-prem, in the cloud, or even on your local machine, it can actually add up pretty quickly. And then the last is when things are time consuming and slow and they cost a lot of money, they become incredibly frustrating. And so that's really just kind of a pain point that's very real and very tangible. And the key thing here is that as a data scientist, you want to be able to actually decrease your time to insight. So you want to decrease your cycle time, and you want to be able to speed up how many iterations you can fit in, because when you do this, this actually allows you to figure out things a lot quicker and then drive forward towards a model that can go into production much sooner. So NVIDIA's solutions really address these challenges. So in terms of the outcomes that you can actually see when you implement these, the first is significantly less waiting. So at Oak Ridge National Labs, they experienced a 215x speed up using GPU accelerated XGBoost. Now this is a speed up, so that means something that took you 215 hours before now takes you 1 hour. So that's significant. Secondly, a global retail giant saw a $300 million cost saving by using an improved model that was able to allow them to more accurately and effectively manage their inventory. So by just having a better inventory management through a model, they were actually able to just get significantly better results. The last is a streaming media company. They were able to realize $1.5 million in infrastructure cost savings. So again, this is real money that was put back into their pocket. So all across the board, you see less waiting, better results, all for less money. So the data science process, what does this really mean? All of us that have worked as data scientists, we've seen the full gamut of the entire flow of a data science workflow. So the first is you classify the problem. What are you actually trying to answer? What are you trying to figure out? Then you acquire the data, which is a really critical part of that. Then you actually have to process that data and get it into a form that's usable, because raw data is actually rarely usable. Then you actually go ahead and model the problem. You validate and execute on typically a test set, and then you actually push the model into production by deploying it. So the key thing that I kind of point out here is that a lot of people associate us at NVIDIA with kind of the modeling the problem and even the validating and execution. And the reason for that is because when you're used to dealing with PyTorch and TensorFlow, that's really where this happens. And what I want to challenge the thinking is that GPUs can actually be used very effectively for this entire workflow. And I'm going to go into very specific examples of how that can be done. So the real power here is being able to use the parallel processing abilities of the GPUs in order to tackle really the earlier parts of the data scientist workflow by allowing speeding up of data processing, and then actually even using the GPU for a lot of things that aren't associated with a GPU compute, such as your pandas data processing, your scikit-learn model training in random forest, malicious regression, whatever it might be. You can do all of those using accelerated processing. So I'll go into what that really means. So a workflow that many people are definitely familiar with is the kind of the default Python workflow. So in a Jupyter Notebook environment, you've got obviously at the top your data prep, model training, visualization, and then what everyone really knows is your pandas data frame, right? You go ahead and you use your pandas data frame, and pandas works really well up until you have a really large data set, and then it takes forever to load the data into the data frame. And if you somehow get lucky and you can load it into the data frame, it takes forever. But worst case scenario is it takes forever, and then the data frame breaks because it actually can't fit all the data into that data frame. So that's a real problem. And then the second is scikit-learn. Everyone's familiar with scikit-learn, and you can actually go ahead once you've got your data inside a pandas data frame. You can actually use scikit-learn in order to train on that. But again, scikit-learn you can run into the issues around model training times, and the amount of time that it can take you to do that. I know I personally have set up some of my notebooks to execute at the very end of the day, so that when I come back the next day, they're ready for me to actually go ahead and use, because that's how long that they take. And then obviously graph analytics, network X, deep learning, TensorFlow, PyTorch, and visualization. The key thing to point out here is that all of these are underlined by CPU memory, because that's really the limitation that I'm trying to get at here. You'll notice this yellow box Dask. I'll come back to that in a bit and explain a lot more about what Dask does. But you can use Dask with pandas and scikit-learn. So RAPIDS is really a GPU accelerated way to improve and speed in your entire pipeline. So instead of pandas, we can actually go ahead and use cuDF or cuDataFrame. Instead of scikit-learn, we can actually go ahead and use cuML or cuMachine Learning. Instead of network X, we can go ahead and use cuGraph. And then all these other things here, deep learning and visualization. And the way that we achieve this is that in order to get maximum acceleration out of GPUs, you have to use a pretty low-level language that we created here in NVIDIA called CUDA. And it's written primarily in C and C++. But with RAPIDS, we actually took care of the back-end plumbing that links the Python directly to this. So you can actually go ahead and stay in Python. You don't have to go and back out to these lower level primitives that are just painful to deal with. We've taken care of that. And so that really helps things out here. And then the other thing I'll point out is this is all underlined by Apache Arrow and GPU memory. So one is the GPU memory. You're able to go ahead and take full advantage of the GPU memory on a particular GPU, so that can be a significant boost. The other thing here is Apache Arrow. So Apache Arrow is an in-columnar data format created by Wes McKinney, the creator of Pandas, and it's really focused around allowing you to be able to move your data in and out of wherever it is you want to be able to, as easily, as seamlessly, and as quickly as possible. So we've really built RAPIDS to have full interoperability with whatever stack, with whatever workflow that you're used to using. So RAPIDS allows the full acceleration and the full benefit of the PyData stack with the power of NVIDIA GPUs. What's Dask? As I mentioned earlier, and you saw it on both previous slides. So the simplest way to explain Dask at a very high level is that it allows you to scale out across multiple CPUs, across multiple GPUs. Here's an example. So let's suppose on this right side, I'm trying to analyze a bunch of tweets from Twitter. And I've got a bunch of tweets, and they're all from January of 2016 up until May of 2016. Now, if I'm not using Dask, I'm going to hit a problem here. And the problem I'm going to run into is I can only fit the tweets from February of 2016 into a pandas data frame, into a one single pandas data frame. Because if I do more than that, it's going to break. Now, if I go ahead and I use Dask, I can actually scale out across multiple CPUs, across multiple GPUs, and I can fit all of the tweets from January 2016 up to May 2016 in memory at one time. So Dask really allows you to scale out and to get real, fit all of your data in memory at one time very efficiently, very easily. And the great thing about Dask is it takes care of the backend distribution, execution. You don't have to think or worry about any of that. It just makes it very seamless. So you're still staying in Python, and it's taking care of the scheduler and all of the meticulous parts on the back end for you. So it really makes life a lot easier. So what are we really trying to do here? So on the lower left side on the PyData, this is where most people are right now. They're very familiar with again, pandas and scikit-learn, a single CPU, and you're limited to the in-memory data ability of that one CPU. Now, what we can go ahead and we can do is we can scale up using RAPIDS. So that's just by switching from pandas to cuDF or from scikit-learn to cuML. And then if we were to stay in PyData, but we were to scale out, we can actually go ahead and use Dask with that. And again, that would just be a Dask pandas data frame, a Dask ML. But the real power is when you actually both scale up and scale out. So when you use RAPIDS in conjunction with Dask, this allows you to get the best distribution, the best memory ability, and the best training times across the board. So you really get the full scale of a cluster. And this allows, again, we can do up to 10 terabytes memory, even more than that. And the lowest training times possible. So the benefits are really, really, really significant when talking about production workloads. So what are some real actual repercussions of this? So we're going to go ahead and look at a 200 gigabyte CSV data set. So if we did this on 20 CPU nodes, this is about 8,700 seconds. So this is actually roughly about 2.5 hours. And then if we were actually to go ahead and increase it to 100 CPU nodes, we're looking at about 1 hour here. And if we were to actually go all the way fully on GPUs, we're taking this down to 2 minutes. And this is across all data load, data prep, data conversion, and then training on XGBoost. And then the similar story when it comes to cost. On the 20 CPU nodes, we're talking about $23. On 100 CPU nodes, we're talking about $42. And then the cost drops all the way to $2 when you're going ahead and you're using GPUs in order to do this. So effectively, the takeaways: 16 AM100s provide more power than 100 CPU nodes. There's a 70x faster performance in similar CPU configuration, and then 20x more cost effective when compared to similar CPUs. Accelerated pre-processing. This is for cuDF. So what you're looking at on the right side here is, again, these are speed ups. So on this first bar, just to say what this just means, if it took 970 hours before, it now takes 1 hour. So these are three very common operations that people might do with data frames: merge, putting two data frames together, sorting a data frame by one particular feature, group by, grouping by a particular feature, things that everyone's probably familiar with. And then what you'll notice here is these are significant speedups. So for merge, we're talking about 970. And then for sort, we're talking about 370, and for group by 330. The other thing I'll point out is that you'll notice, so 10 million rows versus 100 million rows, basically the speed up increases with more data. So the parallel processing ability of the GPU really begins to shine when you talk about larger and larger and larger data sets. And that happens in pretty much every single scenario: merge, sort, and group by. So this is really a very powerful way to get acceleration that's real. So scikit-learn and cuML. So here, what you'll notice is this is just for XGBoost, but we're looking at 20 CPU nodes and up to 100 CPU nodes. Again, taking a significant amount of time. And then with GPUs, we're able to take this down to 1.5 minutes. So again, this is some really, really serious acceleration. And then we've got a significant number of algorithms that are supported by cuML. I'll show those later to give you a sense of what's really you can expect to see. But quickly, it would be pretty much all regressions, all classifications, so all decision trees, random forest, logistic linear regression, SVM models. There's quite a bit of support that's built into QML. And then blazing SQL. So SQL workloads are obviously, kind of where we spend a lot of our time and have to be able to use in order to see the benefit. But what you'll see here is that, when we're talking about 3.8 gigabytes, and then for blazing SQL, we're going down to less than a tenth of that. And then the same thing with the 15.6 gigabytes, a significant speed up. So you'll kind of see that here. You can actually go ahead, go to app.blazingsql.com and spin up a notebook and play around with it pretty quickly. And then deep learning and the integration of RAPIDS with that. So we've really built RAPIDS to again, as I mentioned earlier, to be interoperable with your entire workflow. So PyTorch, TensorFlow, MXNet, Numba, you really get the full benefit here in terms of staying inside the Jupyter Notebook and then being able to do your data prep, your ML, and then also your deep learning, all using the exact same data format because of Apache Arrow. So what does acceleration mean for your workflow? Well, I've lived in this workflow here where you go ahead, you set up your your data frame, go ahead, let it run, let the data crunch. You realize you have to make a feature, change one feature. You have to restart the whole thing again. Now you have to do the next level of data cleansing, where you remove null or nonsensical values, and then you go ahead and repeat this cycle over and over again. You'll notice a lot of red bars here, and red bars is waiting. If you actually go ahead and you switch to a GPU accelerated workflow, what you'll notice is all those red bars shrink drastically. And now you can actually get into the model training, your model cycles in the same day, and then you can actually just get a lot more done in the same day. So the truth is that this is really about being in the GPU fast lane and being able to get the most leverage out of your day and out of your time quickly and easily. RAPIDS has had mass adoption really across the ecosystem. So on here with contributors, Anaconda, Capital One, and Walmart, obviously NVIDIA as well. And then adopters, same thing, across the board: Capital One, Booz Allen, Mapr, OmniSci, Uber, Walmart. So H2O, it's really kind of across the board. And then open source, obviously we're built and made to work with a lot of the the relevant players out there when it comes to interoperability and usage. The great thing I love about RAPIDS is that it can actually be really deployed and used anywhere. So you can use it in the cloud, AWS, Azure, Google Cloud, and many other clouds. There are several cloud services such as SageMaker, Dataproc, Azure Machine Learning that offer it as well. And then you can actually go ahead and take advantage of it via the normal channels: GitHub, Conda, and GC. How do you get started with RAPIDS? Check out rapids.ai. We have a bunch of great documents on there. Happy to engage in engineering discussions. And then NVIDIA also has professional services that we now offer to customers. Additional slides I wanted to go ahead and show. These are questions that often come up. So you can use RAPIDS on your personal GPU that you have at home, so your gaming GPUs. This is kind of a rough sketch of all the GPUs that are supported. But for that first question, basically anything that's Pascal architecture or later, which roughly corresponds to GPUs that are made 2016 or later. So if you have a GeForce RTX GTX 1000 or later, 2000, 3000, those are all compatible. In the data center, A100, T4, V100, P4, P40, these all work. So feel free to take advantage of it. But the Pascal architecture or later, and then GPU must have compute capability of 6.0 or more, and I can go into what that means. In terms of QML, again, the algorithms that are supported, as I mentioned earlier: classification, regression, decision trees, random forest, logistic regression, SVM, inference, random forest, gradient boosted decision trees, inference, FIL, force inferencing library, pre-processing, target encoding, cross-validation, clustering, decomposition, and dimensionality reduction, k-means, db-scan, spectral clustering, singular value decomposition, and TSNE. and then cross-validation, hyperparameter tuning. There's more to come. We're always adding to this and trying to add in more and more support. But this is a great starting point, of course. And then accelerated graph analytics. So this is really about giving people the ability to do graph analytics at scale effectively, quickly, and easily. So right here, what you'll see is some benchmarks around this, but the long and short of this is that we have a library called QGraph, which allows you to scale out to multi-node, multi-GPU for graph problems. So PageRank and others are all kind of supported there. Stream processing. So anyone who's familiar with streams, it's a Python library for stream processing, but we actually basically GPU accelerated this and created a library called QStreams that allows you to get the full acceleration using GPUs. So basically, you can do multiple stream processing at once, and these are really the TCO improvements that you can see here, depending on what you're doing. But you can expect to see up to a 4.5 TCO improvement when it comes to how much you can save in terms of the stream processing. And last, this is for NV Tabular and a specific implementation of QDF, QDataFrame, and Dask for tabular data learning problems related to recommender systems. So this has been a really great usage of RAPIDS, but really it's about tabular data processing, I/O bound scenarios with recommender pipelines. And what you'll notice here is the speed ups are really again crazy. So we're looking at 100x speed ups for large scale ETLs, depending on what your baseline is. This here is Spark plus Spark CPU ETL, and then for every kind of benefit that we incorporate by using NV Tabular, we get significant speed up. And then if you were to implement the very last part of this, which is huge CTR, which is a deep learning framework similar to PyTorch, but that really works even better on GPUs. You can get even more acceleration, but the benefits that are realized just from using NV Tabular over using Spark ETL are significant. Spark CPU ETL are significant. So thank you for joining the session today, and I'll be happy to take any questions now.